there is a feeling that machine learning is the domain of computer science graduates, or at least computer science majors. That is not really true. I think machine learning has found its way into almost all disciplines, including medicine, chemistry, physics, engineering, almost all areas of engineering, and we are just standing at the beginning of the time when this is going to really explode into thousands of different sub applications. So this is a very good time to get into this field, in my opinion, given the increasing interest in this area. And that is not to say that we should throw out our old domain knowledge, which has been gathered very painfully over the past 200 or 300 years, and completely go over to data-driven techniques. So my talk will focus on how can we pick the best from both the worlds. That is, pick the best of domain-informed, learning that we have over the past several hundred years, and to combine it with the data-driven techniques that are, really mushroomed in the last 10 or so years. Okay, so having said that, I think I would all encourage you to write to me. I think Mr. Gurpal will give you my email address. So please feel free to write to me if you have any questions. I will also keep my talk very short, in the hope that we can engage in some kind of interactive discussion, which I think will be even more useful than just me talking all the time. So having said that, let me share my screen and introduce you to this topic. Can you all see my screen?
Yes, sir.
Okay.
It's visible.
It's visible? Okay. So I'm going to talk about physics-informed machine learning, and one of its important applications, which would be the digital twin. So let me. Okay. So this is roughly going to be the plan of my talk. In the first part, I'll talk about physics-informed neural networks, and I will also tell you how I, as an aerospace engineer specializing in computational fluid dynamics, almost accidentally got into this topic. So I'll talk a little bit about traditional reduced order surrogate models, and then the latest application of physics-informed neural network to this problem. And then a couple of interesting problems like inverse problems, uncertainty, how to improve simulation accuracy, simulation speed, etc., using this technique. So I'll give you two case studies that I've personally done. Then in the second part, I'll talk about a very emerging and important application, namely the digital twin, and then we'll conclude, with a summary. Okay. Okay, so basically, part one is physics-informed neural networks, and it's all about deep machine learning augmented with domain knowledge. Okay. Uh, so what really are artificial neural networks? Okay, it's a decades-old technology. Even my roommate back in 1990 was working on neural networks, and so neural networks have been around for they had already been around for 20 years when he started working on that. So basically, it's several decades old. So why are people getting suddenly interested in a very old technology in the last 12 years or 10 years or so? Okay, so it got a shot in the arm around 2012. Now, what is the interesting aspect of artificial neural networks. So number one, it's got the mathematical property in the sense that it is a universal function approximator. Okay, so I think most of us have learned about data fitting and fitting a straight line to data, especially least squares linear, straight line fitting to data. Uh, what neural networks does, or what we do with neural networks, is pretty much the same thing, except that neural networks are nonlinear functions. They are not linear functions, they are nonlinear functions. So they can fit many more classes of data more accurately than just a straight line. Okay. On the disadvantages side, they need lots of data for training. And lots of data for training, it also means lots of good computing horsepower or significant computing resources for the training. And these are the two reasons why neural networks did not really become viable or popular till about 2012. Okay. On the advantages side, once you have a trained neural network, its evaluation is very rapid. A few milliseconds as opposed to maybe hours of computing time using traditional simulation techniques like CFD and so on. Or if you're going to do experiments or actual measurements, it takes even longer time and is even more costly. Whereas here, this is very cheap and the evaluation is very rapid. So here I show you a schematic of a neural network with 3 layers. So reading the picture from left to right, on the left you have an input layer, which is where you give all your x, x1, x2, x3, whatever you want as inputs. And on the rightmost side, you have the output layer, all your y. So y is a function of x. So the function, however, instead of being a traditional function like sine or cosine or straight line or whatever, is a nonlinear function represented by a neural network. So in between the input and output layers, you have at least one hidden layer. And if you have more than one hidden layer, if you have many hidden layers, then it's called a deep neural network. Otherwise, it's a shallow neural network, but you should have at least one hidden layer to classify as a neural network. Okay. Okay. Now, I will not go into the mathematics behind neural networks at this stage because we want to have a discussion at the end of this talk, and I want to keep time for that. But what is it that we do with physics informed neural networks? Now, in the previous explanation of my neural network, you have seen you need lots and lots of data for fitting a neural network, for fitting the parameters of a neural network. But in many sciences and in many application domains like engineering, it's very expensive and time consuming to collect good quality data, right? How much time does it take to set up an experiment, put sensors and measuring instruments, calibrate it, get and collect data? It'll probably take you the better part of 1 or 2 years, probably a master's degree to do an experimental setup and measurements and all that. But so you don't want to, so data is very time consuming and expensive to collect in engineering and the sciences. So is there any way we can short circuit this process and still do and get what we want without going through all that expense? So the answer to that, one answer to that, is a physics informed neural network. Now, on the green, in the picture I have shown you here, on the green side, I have shown you a typical fluid flow problem with boundary conditions and fluid properties. So when you go through the neural network, and if you have a trained neural network, you get the velocity components, pressure, and so on. Now that is a data informed approach, pretty usual neural network kind of approach. Now, on the right side in the pink color, I have also put in the governing equations of fluid flow, equations of mass continuity, momentum, and so on. The second equation I have shown there is the full vector momentum equation. So all three components of momentum are there. So you pass it through the Navier-Stokes or the governing equations, So you end up with right hand sides like R1, R2, R3, R4, and all that, which should be zero, right? Mass conservation adds up to zero. No net mass can be created. Momentum conservation plus forces add up to zero. No, F equals ma basically. So all this should be zero. But in the process of, when you start out with training a neural network, this will not be zero, because the neural network doesn't know any physics. It will give you some crazy answer. You put it through the Navier-Stokes equations and get non-zero values for the residuals. Then you train the neural network through some optimization procedure, so that it so-called quote unquote learns from the data. As I mentioned there, learning from data is nothing but an optimization procedure. And knowledge of the physics means, once it is trained in this manner, it will ensure that the residuals of the Navier-Stokes or the governing equations are also minimized. Okay, you cannot bring it down to zero. That is a very ideal situation. But for all practical purposes, you can make it very small, so that you end up with a very good approximation to the governing equations. Okay, so automatic differentiation of the solution gradients gives you a gradient based optimization procedure, whereby you can improve the parameters of the neural network and get a trained neural network, which not only has learned from the data but also satisfies the governing equations of the problem. So here are some of the research groups that are working on physics informed neural network. I'll refer to it as PIN from this point onwards. So it was invented, or the name was coined by Racy et al. From Brown University. And here in India, Professor Balaji Srinivasan at IIT Madras is working on that. And Professor Prabhu Ramachandran at IIT Bombay, Professor Sauvik Chakravarti at IIT Delhi, and Mr. Gurpan also told me about another person in Bhopal who is working on that. So basically, these are the references, and I think if you are interested, I can share my presentation with you, so you don't have to note this down. Okay. Now, why do we go through all this procedure? Now, as engineers, we like to explain our results. We don't want a black box which has been trained using only data, right? So we want an explainability of the results. So results can be better understood because they obey the governing equations, and that we are all familiar with. And secondly, it's more robust and more accurate when you operate it outside the range of its training data. Now, as you know, engineering data is very expensive to collect, so you are unlikely to get enough funding to collect such a huge range of training data. So inevitably, in practice, in the field, you will evaluate the neural network outside its training data. So then it's likely that it will be much more robust and accurate when you do that. So it works with small data, not necessarily big data, and it can even be made to work with no data. And if you don't have any data, then it can be viewed as a meshless method for solving your governing equations. I've mentioned Navier-Stokes equations here, but it can be applied to any set of algebraic or differential equations. Okay. So during the time period 2020 2021, people have been sitting at home, and they have been working on very interesting problems even sitting at home, especially in the PIN. So they have applied physics informed neural networks for turbulent combustion, multi-phase flows, structural dynamics, and so on. And these references are some of the latest ones picking up this explosion in the research activity going on. The third paper is from Professor Sauvik Chakravarti at IIT Delhi. So that's okay. So, and what are the other uses of pins? So they can be trained to fit and calibrate unknown parameters in differential equations. Okay. So now, what do I mean by that? Okay. So consider, for example, you want to simulate groundwater flow. To simulate groundwater flow, you need to know the properties of the soil all the way throughout your domain that you're interested in, and also to a fairly large depth. I mean, you know how deep you have to dig to find groundwater in some locations. So, can you know all these soil properties at a large number of points, say maybe 100 kilometers by 100 kilometers, or even 1 kilometer by 1 kilometer to that depth? Getting the soil properties is accurately is very difficult, right? Or almost impossible. It will be too costly. So what you can do is you can measure water depth at a few points, okay, and then you can try to keep the soil properties, the soil, the hydraulic resistance, as an unknown, or as a set of unknown parameters. And then using the differential equations and measured data, you can fit and calibrate the model. Okay, so this is referred to as either parameter estimation, okay, and or calibration, and some papers refer to it as data-driven discovery of physics. So this is a very interesting problem, and which has potentially a lot of applications. For example, consider if you want to track an atmospheric pollution problem. Suppose a factory has blown up and discharging pollutants into the air, and you want to know where it will go based on wind conditions, and the whole place is full of smoke, so you don't exactly know where the pollutants and poisonous gases are coming from. But if you have a few sensors which measure some data, and you have a trained neural network that has been fit using this technique, you can try to get at least an approximate location of the source of the pollution and its strength. So these types of problems are called inverse problems, and mathematically they are very, very difficult to handle, and very ill posed. So this is physics informed neural networks is a very good way to reduce the cost and improve the accuracy of handling such problems. Okay. Neural networks have been used in uh, cardiovascular flows to obtain patient-specific blood vessel geometry, and to predict the risk of aneurysm rupture in various blood vessels. So, aneurysm is a ballooning of the blood vessel, and if it bursts, then the chances of death are very high, and it does kill several people all over the world every year. So if but the problem is the surgeon has to decide whether to operate or not, and you can have neural networks do a very fast evaluation of the blood flow from the blood vessel geometry and other patient parameters, and compute things like wall shear stress, pressures, and so on, which is very useful data for the surgeon to decide whether to operate or not. Right now, at present, the surgeon doesn't have much data to go on other than things like age of patient and whether he has blood pressure, whether it's a male or female, whether he's a smoker or non-smoker, some 5 6 parameters. But if you get the actual pressures and wall shear stress, the surgeon can make a much better decision whether to operate or not. And even there are non-surgical treatment methods, or I mean not like putting stents. I mean, I shouldn't say non-surgical, but less invasive surgical procedures like putting stents and so on, which can be used to control flow into the aneurysm. So these are all emerging techniques, and very rewarding. You may save a lot of lives this way. Okay. I will skip this. I think. Okay. So let me tell you an interesting story about how I, as a CFD person, somehow got into the machine learning problem. Although my background is in CFD. Okay. So an automobile client came to me. An automotive manufacturer came to me with a very interesting problem. On the right side, I have shown you the picture of an automotive cooling circuit, right? You may have all seen automotive cooling circuits in cars, especially if any of you have electric vehicles, you will see this at, cooling circuit for the batteries and so on. So you can see it's very complex system with fans, radiators, reservoirs, pumps, tubing, and all that. And when you fill the circuit with coolant, air bubbles get trapped in it, right? And these air bubbles are not they really degrade the performance and cause your system to break down, and it's generally not good for the life of the components also. Okay. So they were simulating it using CFD, using 3D unsteady Navier-Stokes plus volume of fluid approach. Yeah, don't worry if you don't know what this is. This is just a very sophisticated technique to do multi-phase flows, like mixtures of air and water or air and coolant. Uh, Typical applications of this. Now these are very resource intensive. Sometimes it taking up to even 3 months. So they came to me to see whether we could reduce the time required to get a solution for this problem. So then we were trying various things, and then we noticed that when we saw the experiment in their lab, we found that the radiator tubes were not trapping much air. Initially while filling, the air would get flushed out, and then it would be, so the air was getting trapped somewhere else. But CFD computations were taking a long time because of hundreds of tubes in the radiator. So we thought, why not replace these radiator tubes with a machine learning model, and then link it with CFD solutions elsewhere in the circuit. Okay. So we started off with projection-based models. Again, don't worry; these are mathematical things, and if you don't understand, it's not. Do not worry about it. We used a technique called proper orthogonal decomposition, and I just show this slide to let you know that proper orthogonal decomposition was a mathematical technique invented by an Indian mathematician named Kosambi in 1943, and it was published in the Journal of Indian Mathematical Society, and nobody really knew about it until about 2 or 3 years ago. And, somebody found this paper, and then, okay, it's not really an invention of Westerners, but our own Indians. So this technique, there were some defects and deficiencies with this technique in the context of CFD. So then we went to a neural network, and I used a type of neural network called long short-term memory network. Again, don't worry if you don't know what it is. It is useful for time-dependent and unsteady problems. So our solution was to train the LSTM with a single tube, and then replace the mesh in all the radiator tubes with LSTM. And then we embedded the train model inside the finite volume CFD code, and we had the machine learning model and the finite volume method exchange data at every time step, and then we were able to speed up the computation by about 30%, which was considered, which the client appreciated very much actually. So these are some details of the training process. I don't want to get into too many details here. Let me skip some of these slides, and I'll go to my second case study. Um, the second case study deals with a concept called predictive maintenance. Predictive, you may all have heard of preventive maintenance of various equipment. Preventive maintenance is when you change the oil in your car after a certain number of miles or after a certain time period, like 6 months or whatever the manufacturers, but if you see, that is really not a very efficient technique. You may not have driven very much, or maybe you were sitting in a cold climate and the oil degenerated, or in a very hot climate and you may have to change earlier than what it predicted, or you don't have to change it as quickly, things like that. So what is really of interest is what is called predictive maintenance. You really see the state of the system. For example, is the oil really contaminated and doing badly? And then based on that, based on measurements of the system, you can then decide to change your oil or do other repairs only when it is required. But however, you don't wait till it actually breaks down. If it breaks down, that's not a good thing, because then there is downtime and all that. And if it is a vehicle or an aircraft, it could pose a risk and loss of injury, or risk of life also. So you want to do predictive maintenance, which is much more efficient. So this is a case study. There is an open data set for this. So the machine learning model was developed to monitor 4 different fault conditions using data from 17 sensors. And the data set is there openly available at University of California, Irvine machine learning repository. So basically, I think you may be somewhat familiar with a hydraulic circuit. This is the original reference for that study. These people also did a traditional machine learning model, whereas we decided to improve upon it and go towards a neural network model. So you have pressure sensors, temperature sensors, vibration sensors, oil condition sensors, and so on. And you take data by simulating various faults in the circuit. Um, so the hydraulic circuit typically consists of a main circuit with actuators and valves and all that, accumulators and all that, and a secondary cooling circuit which is used to cool the oil, because as it does work, it heats up. So you need to cool the oil. So they monitored 4 different types of faults and they have reported all that data. So we decided to fit this with a neural network, you know, and capture all the faults if possible using this method. So the structure of the neural network looks somewhat complex, but it's not really as frightening as you may think it is. So on the left side are all the pressure sensors, flow rate sensors, temperature sensors, vibration sensors, electrical power consumption, and all those things. And as you go towards the right, the network becomes more and more narrow. And at the right, it again splits into two and tells you whether the hydraulic circuit is operating normally or whether there are any faults. If there are any faults, what is the type of the fault? So these are some of the details of the training that we did. And again, don't worry if you don't understand all of it. If you you know if you get in touch with me, I can tell you how to get started in machine learning for engineers. But we got our accuracy was actually too unbelievably too good. So I think it is probably because we were overfitting the training data. I mean, nobody gets 99.9% accuracy in real life, right? So we have probably overfit the training data. So we are doing some steps to introduce some additional errors into the data so that we can get a more reasonable number, which will work in the field also. But what I just wanted to show you a flavor of this so that you could see what is possible with a neural network. Okay, now I go on to a digital twin. I'll quickly introduce that concept, wind up, and then we'll leave the floor open for questions. A digital twin is a complete or comprehensive digital model of any physical asset, device or process or a system. By physical asset, I mean any equipment that you may have. And a process could be any manufacturing process or factory or any of those things. So a digital twin builds up a complete digital replica of that system. It was basically, the name was coined by Greaves and Vickers quite long ago, but I've cited a recent reference here, which is quite interesting to read. So it's an up-to-date and real-time representation of your equipment. That is, your equipment is already in the field, you have instrumented with sensors, you're collecting data, and you're updating the digital model. So it's not something that you do at design time. It is something you do continuously through the lifetime of the product. Um, you know, so our goal is to enhance these models used in the digital twin with the physics-informed neural network. Which we feel will give you. So this is a pictorial depiction of the digital twin. On the top left-hand corner, you have a typical physical asset, which I have shown in the form of a chemical factory with tanks and so on. In the middle, I have what I show as edge computing, which is basically circuit boards and other things which go on your in your factory or on the equipment. It collects data from sensors, which I've shown in the top right-hand corner. Then the whole thing connects through Internet of Things. I'm sure you've all heard of IoT and Internet of Things. So they communicate with that through the cloud and with your database and storage facilities. So that we want to enhance by using physics-informed neural networks for various models, which we feel be accurate and more robust than traditional machine learning models. So why do why are we interested in digital twin? We can use it for condition monitoring, like I showed you in the hydraulic circuit example, predictive maintenance, like I talked about before. You can also do remaining time of life estimation of various parts and equipment, diagnose any faults, and helps you to deal with complex systems, and generally gives you safer and better products, or it will give you safer and better products when it is properly implemented. So a lot of big companies are supporting this digital twin frameworks. GE, Bosch, Siemens, SAP, they are all supporting digital twin frameworks, but none of them use physics-informed neural networks yet. So we want to promote that and bring physics-informed neural networks into the mix, basically. So our vision for digital twin and the physics-informed neural network, when it is properly implemented and becomes popular enough, then no engineered product should ever fail unexpectedly or catastrophically while in service. Uh, I can't help thinking that the Boeing 737 Max would have never crashed with so much loss of life if there had been a digital twin for the aircraft. So basically, let me summarize. I've talked about physics-informed neural networks and how we as engineers can use that very effectively uh, in making our designs better and safer and more optimal, and how we can use it in a digital twin which will make our products and processes safer and better and more optimal. It's a very promising and fertile area for future developments and new applications, and I would certainly encourage those who are interested to really get into this area. And it's not very difficult. As you can see, there is a book called Neural Network for Babies, and you can see the baby reading this neural network book. So I think that should be inspiration for all of us to get into this area. Thank you, and I would be happy to take any questions or discuss anything.
Thank you so much, sir, for that enlightening talk. I'm sure we all have learned a lot about the new topic of physics-informed neural networks. And so I would like everyone to please ask any doubts if you have any in this topic. Or you may post it in the chat box. I will read the doubts, or you can ask one by one. Sir, I
So
had also one doubt.
sure.
Sir, I was just wondering if I were taking a very simple example, like a flow over a plate. So,
Right.
sir, for that, x, y, and time are our inputs for the neural networks, and it gives us the velocity and uh, pressure that we need, the output
Right.
if we design Navier tubes. So, is it possible we can make a Reynolds number an input parameter? So, for predicting the results, we can predict the results for any Reynolds number we want for training one neural network.
Right, right, right. Certainly, you can do that. You can input the geometry of your domain. The if you have constant properties of the fluid, you can certainly put in the Reynolds number. If you don't have constant properties, or if incoming flow is time varying, then it's probably better to give the raw inputs. Viscosity, density, plate length along the plate. Because if you just have a flat plate, if it is aligned with your flow, like your typical flat plate boundary layer problem, then the Reynolds number is a function of the distance
Distance.
along the plate, right?
Yes, sir.
So it's not a
Yes, sir.
single number. So maybe it is more convenient for you to give the raw numbers itself as inputs.
Okay, so I was just taking it example. So suppose if we have Reynolds number as a constant function, uh,
Right.
then that place we can take it. We can predict it a different Reynolds number. Our solution a different Reynolds number
Sure,
by
sure,
just
sure,
one
sure.
place.
You can do some combination of data from either measurements or a CFD code, and then you can train the neural network using the physics informed concept to interpolate the stuff between your data points.
Thank you, sir.
You're welcome.
So, uh,
Okay. Yeah, you're working on wear of bearing due to thermal. Okay, good.
so any more doubts?
Yes. Yeah. I think Mr. Frank, yeah, ISS. What's for thermal energy for CNN? Are you using a convolutional neural network to fit that model? Okay. Okay. You can open up your mic and speak if you want to. So so can you describe your how you have
Sir,
tried to fit the model?
sir, this is Franklin from Anesthesia.
Frank.
Sir, actually, I'm working on thermal images for studying the wear debris and worn out of the bearings, sir.
Okay.
So, can I use ANN to improve the imaging? For example, I have the worn out images as an outcome. I seen the images through same images also. Whether it is
Sure.
possible to use CNN for to improve the characterization studies, or whether to recognize what kind of wear this can be possible through using some neural network system, sir.
Right, right.
Image processing
Yes.
based neural network
CNN
system.
is already, very good at processing images. So if you're using a thermal imaging system, it's quite likely that they're already using CNNs to give you the temperature field.
Okay.
Uh,
Yes, sir.
so most probably inside the software that you use to process the images, it's
Yes.
quite likely that they are already using a CNN inside it. Do you know
Okay.
how that software works?
Sir, actually, in Matlab, I'm working using image processing module, sir. But
Okay,
still, I couldn't very good making getting the output. I couldn't make good outputs out of it, sir. Actually, I'm really searching for new tool or some other techniques to process those images, thermal images.
okay. You can. So you are collecting the images using some infrared camera, right?
Yes, sir. Yes, sir. Using infrared cameras, image process.
And then you are processing those images. Doesn't the camera come with any software which will?
Uh,
Uh,
No, sir. Actually, I'm getting a individual images using some stretch tools. That is like a, bitwise image stitching tools. Only I'm using to make it as a 3D image, complete 3D image.
okay,
No other software is inbuilt in it, sir. I want to know. Actually, in websites, I searched for some good tools for making image recognition, but
yeah.
I couldn't identify anything properly, sir. Can you suggest something, sir?
Well,
For
uh, you you have you yes, there are a lot of open convolutional networks which can process. What is the typical size of your image?
Sir, approximately, yeah, the 4 centimeter or 4 image pixel
No,
is 1200.
pixels. Yeah, number of pixels.
Approximately 2400 cross some thousand, sir. Approximately, because the pixel size will vary to image to image.
Okay. So you will definitely have to use a CNN, no doubt in that,
Okay, sir.
because a regular ANN will run out of memory handling
Okay,
such a large one. So,
okay,
so yes, but you will probably have to train your own CNN for that kind of image. But
okay,
there are many open CNNs
okay,
that you can download,
okay.
and then you can retrain for your problem. But training such as CNN would be quite time consuming and require a lot of computing horsepower. And
Yes.
do you have any way to calibrate the at least a few of those images with the actual temperature?
Yes. I have the control images, sir, to compare those things.
You have the control images with temperature recorded in each pixel.
Yes, sir. Yes, sir.
How many such images do you have?
Sir, actually, I've taken more than 300 images, sir.
Okay.
Uh,
How many control images do you have?
Around 10 images, sir. That's it.
Okay. Okay. For
Uh,
training a CNN, that is very less.
okay.
So you may not get good results if you just train with 10 images.
Okay, sir.
So we may have to do some fairly special techniques to get the kind of accuracy you want out of this.
Okay, sir.
Okay, what does MATLAB do actually?
Sir, in Matlab, I have restored the images and tried to make it as a complete like a 3D image, that is a version-based variation. Like we are using a what we say, the temperature differences, identifying the temperature differences exactly using Matlab, sir. From range from three, actually my range is from almost 200 to 400 range, sir. My temperature ranges.
Okay,
So from that image, based on the color prescription, I'm interpreting the temperature range, sir. That only as of now I'm doing.
okay,
But to make it to the next extent, that is, I want to study also the what is the O note first, in which area the O note occurs, or which area the temperature starts to rise up. That I want to
okay,
identify exactly
okay,
like a motion pattern. This
okay,
thing I couldn't do now, sir. Only the particular image recognition only I'm doing for a single image, not
okay.
for a clubbed motion, or for not for a club of 10 to 300 images. I couldn't do for a.
Okay. Where is the actual difficulty? The MATLAB software doesn't give you the correct temperatures, or it's not able to load it. Or...
Yes, sir. Yes, sir. Actually, the software doesn't. For a single image, I can interpret very clearly. The
Okay,
results are matching with my theories. But
okay.
in case of the processing 200 to 300 images at once is not possible, sir.
That you will have to use special techniques. I don't think there is any computer which can load 300-400 images of that size in one shot.
Oh,
You
okay,
will
sir.
run out of RAM. You know. Uh,
Yes, sir. That's why I made that 200 images into a single image. Like we are what we are using in a brain scanners or CT scanners and all. We are clubbing individual frames to frame a one group photo.
see,
Same way
see,
I'm
whatever
doing.
it is, whatever it
Okay.
is,
Okay.
uh, you said about 1400 by 1000 pixels, right?
Yes, sir.
1400 by 1000 pixels, and you have probably an RGB image with red, blue, green, blue channels, right?
Yes, yes, sir.
So that is 1 byte each, right? Two.
Uh,
So
uh, Almost, sir.
right.
Yes. Mm.
So basically, let us say it will use 32 bits for that. So basically 32 bits times 1400 times 1000 times 300 images. I
Okay.
don't think I don't think any modern day computer has enough RAM to load your image up with that.
Okay. Okay,
Okay.
sir.
So that approach will never work. Okay.
Okay. Okay, sir.
I don't think anybody will build also in future a computer with that much RAM for on one single computer. So you will have to go for some sort of distributed processing of these images if you
Okay,
want to
sir.
process all 300 at the same time. But
Okay. Okay,
my
sir.
question is, why do you want to process all 300 of them at the same time?
Sir, actually, my work is just to interpret those temperature gradients for a single image and analyzing that. But
Yes.
after getting idea about the CNN, I thought it is possible to process those images in a collaborative, there is a collective manner. I felt that's why I asked, sir.
Okay. What
Uh,
you should do is you should process the 300 images one after the other. You should
okay,
not try to process all of them at the same time.
okay, okay, sir.
Okay, so process one, get your extract whatever temperatures you need,
Okay, sir.
put it on disk, store it somewhere, process the next image, and so on. So
Okay, 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 fine, sir.
otherwise, whether you use machine learning or any traditional method,
Sir,
the end
actually,
effect will still be you will run out of memory.
oh, okay, okay, sir. Uh, Sir, as of now, currently, which one is good for a research scholar, sir? Any tool for machine learning?
Any tool for deep learning? No, you will have to learn Python, and you will have to, I think, do. I mean, I myself did when I wanted to enter the subject
Okay.
about 1.5 2 years ago. I myself did some 4 5 courses from Coursera.
Oh, okay, sir.
Okay, and I myself learned Python to do all these, to try out all these things.
Okay, sir. Thank you, sir.
Okay, yeah,
Thank
welcome.
you. Thank you so much.
Sir, we have one more doubt
Sure.
from Miss Lisa. Sir, it says, Sir, I wanted to know about the future scope of physics-informed neural networks in field of material science.
I think future of physics informed materials, physics informed neural networks is good in almost all disciplines. I think in material science, what are you looking to do modeling or something at the molecular and atomistic scales, or anything in particular that you have in mind? If it is difficult to type the answer, you can unmute yourself and talk.
Sir, I think she got disconnected maybe due
Yeah,
to
yeah,
network
probably.
issues.
Yeah.
Uh, uh, so anyone else having doubt? So you can just switch on the mic and ask.
So,
Sir, is there
So I
any
guess
criteria like a minimum amount of data is required for processing the CNN?
well, there is no hard and fast minimum as such. In fact, the more you have, the better. So I would depends on the application also. Any particular application you have in mind?
Like material informatics?
Which informatics?
Material informatics.
Material informatics. I think you will need plenty of data. Yes.
Okay.
I, um,
So, like normal ANN, you can make use of with a very minimal data also, like 25-30 data if you have means that can also be
no,
processed.
that's actually that is not the best practice. What you should actually do is you take your data and split it into three portions. Okay. So typical splits are in the range of 80%, 10%, 10%. 80% of your data you can use for training. 10% you use for validation. Then typically you will not stop with developing just one neural network. You will develop a collection of models. Okay, some at least 3 4 neural network models with different
Okay.
numbers of neurons and different layers and all that stuff, or different activation functions. At least 3 4 models you will develop. Then once you have all these validated, then you run it on the test data, the last 10%, to see which is the best model. So that is the way. You can't really say, okay, for this application it is okay, 30 data items is enough. For this one I need 2000, for this I need 1 million. So that is not the best practice. The best practice is to actually do the 80%, 10%, 10% splitting, and then actually validate your model on test data.
Okay.
So in that case, you may find that you actually need more data than you may find that you really need much more data than you had originally anticipated. Typically, we are now working with data items for that hydraulic circuit. The original experimenters had collected 2,205. They had done 2,205 experiments, and we find that our neural network is so deep that I think we are overfitting it. Okay, so we are adding some random noise to the original data and expanding it to about 2 lakh data items. Okay,
Okay.
so I think that is the scale we should start thinking of when it comes to neural networks, especially deep neural networks. I think we should think in terms of 10,000s, lakhs, those kind of numbers. And then still, of course, we should do the training, test, validation, and split as 80%, 10%, 10% at least. So that would be a better way to proceed in my opinion.
Okay, sir.
Even for the CFD problem of radiator tubes, we did at least 68 CFD runs to generate sufficient training data. So we took every alternate grid cell, every third grid cell as training data and so on. So we must have ended up with a couple of thousand training data finally.
Fine, sir. Thank you.
Thanks.
Sir, just one thing more. I just
Sure.
came into my mind. So, like I told you, I was working on this problem. So, we were working on simulations of a rising bubble. So,
Okay.
sir, the problem we were getting is like we didn't give any data. We just, as you told, analytical solution, meshless solution. We were trying to do that on Heising et al. Have given the bubble problem on that one. So, but we were getting very close results, but our loss function wasn't going less than 10 to the power minus 3 to 10 to the power minus 4.
Well, did you normalize your incoming data? That is,
Yes,
normally
we
when
try.
I do neural networks, I try to normalize it or non-dimensionalize it between either between 0 and 1 if I'm using activation functions like sigmoid or ReLU or something, or if I'm using hyperbolic tan or antisymmetric loss functions like hyperbolic tan, then I try to normalize it between -1 to +1. So
Yes,
did
sir,
you
we normalized
normalize
the
your
data. We
velocity
normalized the
field
data, sir, but we did it from 0 to 3. Oh, sorry, 0
0
to 1 we normalized.
to
Sorry, we normalized in 0 to 1, and sorry, that time steps we gave at 0 to 3. So, sir, we normalized the data, but still we tried many things like getting more points near the bubbles where the initial bubble is there, and like doing the code in such a way that more points will be
so
generated near the bubbles. Still, we were getting almost the same accuracy.
so with the normalized data, your loss function was at what? How much?
Sir, around 10 to the power minus 4. 1 e minus 10 e minus 4.
10 to the -4.
Yes, sir.
10 to the -4 is sort of okay. Maybe you can go to 10 to the -6. Did you try reducing the learning rate and all that? Was it
Yes, sir.
oscillating?
No, sir,
Okay.
not oscillating, sir. I tried it doing many times, but it was
Oh,
almost
it
constant
was
every time.
almost constant. It's not going down any further.
No, sir. So it was mostly due to, I guess, it was happening in the boundary conditions that were given, because we were doing a multi-phase problem. So you were using deep XGE, if you are familiar for coding. So, sir, like what we were doing is like the boundary conditions, we were getting a loss very high in one boundary condition.
Well, what you can try is how many layers did your network have? Hello?
I just Hello,
Hello?
yes, sir. Sorry, sir, I couldn't.
Yeah.
Sorry, sir, I got disconnected for a while. Yes, sir.
Oh, okay. How many layers did your network have?
Sir, it was having 50 into 9.
15 layers or so? Okay.
50 into 9.
50, okay. And what was the activation function you used?
Sir, it was tan H.
Okay, damage. Well,
Sir,
you had
the results we
normalized.
got very close.
Did you normalize the density? Did you normalize all the variables?
Yes, sir, we normalized everything in a
Okay,
dimensionless format.
in a dimensionless format. Okay,
Yes, sir.
and it still was hanging around 10 to the -4. Okay,
So 10 to the minus 4 was literally, I would say, it was 10 to the minus 3 more of like just
okay,
near to 10 to the minus 4, I would say.
okay. Adding more layers did not help.
No, sir. And also, sir, like we were doing on using Google what Colab, so it was taking too much time, sir. Like
Yeah,
around,
it will
we
take
were doing
time.
a normal laptops from
And
home, so
yeah,
like it was going on for
time it will
days
take.
sometimes.
Yes, that it will do. How many epochs did you run?
50,000, sir.
50,000.
Yes, sir. Sir, like generally,
50,000 is not much. How much training
we
data
used
did you
for
have?
So training data we made around different points in domain and around 20,000 in domain, 10,000 on boundary, initial 10,000 and test points 15,000.
And your last function was very high on the boundary only?
Yes, sir. Exactly on one boundary condition, sir. Like in which we defined the bubble, from which we defined the initial place of a bubble. At that place, we were getting 10 to the power minus. Other all were around 10 to the power minus 5 or minus 6, but only at one place we were getting 10 to the power minus 4 or 10 to the power minus 3, where we defined the bubble, initial condition of the bubble.
So that was exactly on the boundary points, not on
Yes,
the
sir.
field
No,
points.
sir. No, sir.
Only on the boundary points it was not able to catch it properly.
Yes, sir.
Mm, I don't know. Offhand, I cannot think of any reason why only those points should be off. Was the bubble shape slightly funny or something like that? Was it?
Sir, it was the answers that we got were very good, like very comparable to the results from what we were checking it from. Like, but the only thing that we were trying to get is if we can get a better loss function than 10 to the power minus 3. That too because of just one boundary condition.
Um, this 50 layer network, that is the biggest you tried?
Yes, sir. Because after that, like the system was crashing because we didn't have too much of processing power.
And, yeah, dense network, I don't think you can do more than this. It will
Yes,
run out
sir.
of RAM, run out of memory. Um, what you can try is, I suppose you can try some graph neural networks, which will
Okay, sir.
let you do work with sparse data. So you may be able to, um, maybe did you try different activation functions?
No, sir, we didn't try that. We just did
Sometimes
manage.
that helps.
Okay, sir.
Is there anything funny about the data at the bubble that makes it, uh, you know, like that?
Yes, sir. Like, just there was one problem initially that we were facing, like how to describe the bubble. So we just made a sharp boundary layer condition. Like, initially we took the bubble as spherical, like we were doing 2D, so circular. So we defined it a very sharp boundary condition. So it was just not like. Sir, I will,
Yeah.
if possible, sir, I can talk to you on mail. I will show you the
Sure, sure,
conditions.
sure, sure.
Okay, sir.
I think there is, yeah, there is one more question: how to use neural networks in the process of heat treatment? I think, right?
Yes, sir.
So first one was in the field of material science. I can say it's a very good scope in the field of material science. Please tell this person if uh, they are not online at this time.
Ye- Yes, sir. Probably network
So
issues, sir.
I think somebody is asked about how to do it for the how to use this neural network. I think we'll have to share some more details of what you want to do. This is then I'll be able to advise you better. Right now, I can say yes, it can be used very effectively. But if you give me a specific problem to advise you on, I can do that. Okay, Mr. Rajgopal, right? Yeah, Mr. Raj. Yeah, yeah, it can certainly be used, no doubt in that. But if you give me a more detailed problem description, I can advise assist you better.
Sir, I will, if possible, I will share your email ID so they can ask you.
Sure,
You're fine
sure.
with that.
Let me do that. So I just shared my
Uh,
email.
Thank you, sir, so much, sir.
You're
So,
welcome.
like, we're going for the conclusion now.
Okay.
Thank you, Dr. Rao, for clearing all the doubts. And it was very great to learn about this new topic. Also, we thank Mr. Vinod, sir, for his presence. So I have shared the feedback link in the chat box. Everyone, please be sure to fill up the feedback link if you need the certificate, and we will be sending you the certificate in 1 week. So also, if you also for the student of SRM, if you want to be a member of a chapter, you can contact us from Instagram. So thank you for joining our today's talk, and we hope, sir, we can get more talks on this topic with you, sir.
Sure.
Thank you, sir.
Sure. Thank you.
Thank you, sir.
Thank you.
Thank you so much, sir. I will just ask that Professor Dr. Manoj to and share his email ID with you, sir.
Sure.
Sure, sir. Thank you, sir.
Sure.
Thank you so much, sir.
Thank you.
Now sir, we'll be ending the meet, sir. Thank you.
Sure.
Yes, I don't have the. So I guess I don't have the access to, and I got disconnected. So someone else became the host. So just we can just leave. Thank you, sir.
Sure.
Hello.
Yes, sir.
Gurubha, thank you, sir. Thank you very much for arranging this excellent program.
Thank